Hello children, I hope you're all fine. Some of you had sent tried the numericals that we discussed yesterday, and I hope you understood the concept. So those are not right. Make sure you try it today so that you'll be able to understand it much better. Okay. Now, we have studied till this non-ohmic resistors, and I told you this graph is specifically of a junction diode. One example of non-ohmic resistor is junction diode, and this example is specifically of that example only, okay, of junction diode. Okay, so keep that in mind. Okay, now there's another term called dynamic resistance. Dynamic resistance. Now, in case of curve like this, now the main difference between ohmic and non-ohmic resistor is, in case of ohmic resistor, because you have a straight line, like you have a linear proportional line, if you find slope anywhere, if you find slope at any point, I can choose these 2 points, I can choose these 2 points, I can choose this and this. Slope will be same at all points. At all points. Okay. So what does it imply? That it has only one resistance. Okay. Resistance is same throughout. Okay, temperature should be constant. Then for ohmic resistors, resistance will remain the same. On the other hand, for non-ohmic resistors, because its shape is like this, at different points the slope will be different. Okay, so resistance at this point, maybe when it was 5 volt, resistance will be different. Maybe here it is 10 volt. So at every point, you have to draw a tangent and then find the slope of the tangent, and it will be definitely different. So this kind of resistance is given a name called dynamic resistance. Dynamic resistance, because the resistance keeps changing at different points. Okay, so that one term you can just get familiar with. Then we go to the next topic now. Factors affecting resistance of conductor. Factors affecting the resistance of a conductor. This also you studied last year. Okay, so we'll have a quick recap of it. Resistance of a conductor depends on 4 factors: material of conductor, length of conductor, thickness of conductor, and temperature of conductor. Okay, these are the 4 factors. Now, how they affect? In case of material, you should say good conductors offer less resistance, and insulators or bad conductors offer more resistance. Okay, offer more resistance. The reason being, good conductors have lots of free electrons. Okay, metals such as this, they have lots of free electrons, so the resistance will be less, whereas insulators have very less free electrons and fixed positive charges are more, so they offer more resistance. That's how the explanation goes. Now, length of conductor. If you remember, length of conductor directly affects the resistance. So basically the reason is, as the length increases, the opposition also increases. Okay, as the length of the conductor increases, okay, maybe when the length was this much, there were just 10 positive ions to oppose. Now if you increase the length, then there might be 10 more to oppose it. So definitely with increase in length, the resistance increase. So we can write directly proportional. Thickness, inversely proportional. If you remember, thicker wires have less resistance. Why is that so? It's because in case of a thicker resistance, thicker wire, they have lot of space to escape. They have lot of space to escape. There are positive ions here and there, but because the thickness is more, they can escape. They can find a lot of space to escape. So that's the reason why it is inversely proportional. The thicker the conductor, lesser the resistance. Okay. Then temperature, again directly proportional. More the temperature, more will be the vibration of the particles, and therefore resistance will also be more. Okay, so four factors and how they affect, and the description is given here. Otherwise, if you know, if you have an idea, that's enough. Just one line, if you remember, that's enough. In case of length, you remember, in long conductor, number of collisions of free electrons with positive ions will be more. In a thick conductor, electrons get a larger area of cross section to flow as compared to thin conductor. And then the resistance of conductor increase with increase in temperature, because random motion of electron also increases. Okay, so this is these are the factors affecting resistance and how they affect also. Now, VI graph, next topic is VI graph for a conductor at two temperatures. Okay, so here is a VI graph showing having two lines. Okay, same conductor but at two different temperature. T1 is temperature, T2 is another temperature. The question can be, they'll give a graph like this and they'll ask which one is at a higher temperature, T1 or T2. Now how will you decide? So it is a VI graph. So because it is a VI graph, slope will give you the resistance. Slope will give you the resistance, and steeper the slope, more the resistance. Okay, if the slope is steeper, resistance is more. Now that way, when you compare to these two, this is steeper. Okay, so therefore T1 should be greater than T2, because this one has slope of this is more than this. That means resistance of this is more than this. So we know that resistance is directly proportional to temperature. Therefore, this one will be at a higher temperature and this should be at a lower temperature. Or they can ask you the other way. Draw VT graph of two conductors A and draw VT graph of a conductor which is at two different temperatures, T1 and T2, such that T1 is greater than T2. T1 is greater than T2. Then you have to draw like this. If they would have said T2 is greater than T1, then you should have, this should be T1, T2 and this should be T1. So accordingly you can answer. Okay. Then coming to now, so based on the factors affecting, we saw resistance is directly proportional to length. Resistance is inversely proportional to area of cross section. Now, the first two factors, that depends on the nature of material, and temperature will leave it, but the main thing is directly proportional length and inversely proportional to area of cross section. Now, when I combine these two, I get resistance is directly proportional to L upon A. Now, to remove this proportionality sign, I introduce a constant. Okay, rho, it's not density. Okay, this rho is called specific resistance. Specific resistance or resistivity. Specific resistance or resistivity. Okay, so this becomes the formula for resistance. R is equal to rho L by. From Ohm's law, we have the other formula, R is equal to V by I. Okay, that's based on Ohm's law. This is based on the length and area of a conductor. If we have to find its resistance, we have to use this formula, R is equal to rho into L upon A, where L is the length and A is the area of cross section. And rho is called specific resistance or resistivity. Now, what is specific resistance? Every material has a particular specific resistance that depends on its nature. Depending on its nature, every material has a particular specific resistance. Now there is a table here. Okay, this table has the specific resistance of some of the common substances. Okay, they put them in groups: metals, alloys, semiconductors and insulators. Okay, so if you see specific resistance of metals is low. Okay, specific resistance of metals will be low. Okay, and it is very low for metals, and when you see semiconductors it is low, and when you see insulators, you can see the specific resistance is very high. Okay, so for metals it is very low. Okay, specific resistance is very low, 10 power minus 8, and for insulators it's very high. Then in between comes alloys and semiconductors. Okay, so semiconductors specific resistance are less than metals. Now what are semiconductors? So the word says semiconductor, means partially it will conduct. Actually it's between conductor and insulator. It can conduct partially. Okay, so they are called semiconductors. Examples are graphite, germanium, silicon and all. So their specific resistance will be this range. So specific resistance of a substance is its characteristic property. Characteristic property means it's an inbuilt property. Copper means it will have a particular specific resistance. Silver will have a particular specific resistance. So it is its property. It is different for different substances, of course. It is very low for metals and always low for semiconductor, but very high for insulators. Okay, very low for metals, low for semiconductors, and very high for insulators. Okay, and now so this is what we have been seeing. This is the formula. R is equal to rho L by A, where rho is a constant called specific resistance or resistivity. Then little more about specific resistance. Now the formula, because R is rho L by A, the formula for rho will be R into A upon L. So this will be the formula for specific resistance or resistivity. Now what about the unit? Now unit of rho will be, unit of resistance is ohm, unit of area is meter square, and unit of length is meter. So meter and meter will get cut. So ohm meter is the unit. So formula for specific resistance is rho is equal to R into A upon L, and its unit is ohm into meter. Unit of specific resistance, ohm meter. Now come to factors affecting specific resistance. Okay, now specific resistance depends on just two things. One is its characteristic property, means it is different for different substances. So this one. Second one, specific resistance depends on its temperature. It increases with increase in temperature for metals, but it decreases with increase in temperature for semiconductors. For some alloys, it is practically constant with change in temperature. Okay, so see very carefully. For resistance you have four factors. Factors affecting resistance you have four: material of conductor, length and thickness, and temperature. Now these two, material of conductor and temperature, okay, these two are the factors that affect specific resistance. Okay, these two factors only affect specific resistance. Okay, so the thing you should know is, if I have suppose a copper wire, okay, I have a thin copper wire. One is I have a very thin copper wire. Another one, I have a copper vessel. Okay, I have a copper pot. Now, okay, you can imagine how heavy it will be and how light it will be. What about the specific resistance of these two? They will be same. Specific resistance will be same. As long as they are made of same material, if both are made of copper, specific resistance will be same, but resistance will be different. Why? Resistance depends on length and area of cross section. They all affect the resistance. So therefore resistance of these two will be different, but their specific resistance will be same as long as it is made of copper. Irrespective of size or shape, only thing that matters is the material, and temperature of course should be same. I hope you're clear with this two things, resistance and specific resistance. Okay. Now, now what about this? So this is also a fact that you should remember. In case of metals, with increase in temperature, resistance increases. But in semiconductors, it's the opposite. Resistance decreases with increase in temperature. So when you study about semiconductors, you will understand. Right now, you just take it as a fact. In case of semiconductors, resistance decreases with increase in temperature. Now, alloys are very, very unique in this, that their resistance remains practically constant. Practically constant means even though temperature changes, the resistance of constant and manganese and all will not change much. It will not change much. Now this makes it very useful in, if you remember rheostat, construction of rheostat rod, last year we started. Okay, there is a wire on it. So it will be a nichrome wire. This wire is basically, resistance wire is basically made of nichrome. The reason being, it's an alloy, and alloys have this special feature that their resistance remains practically same with temperature, with change in temperature. Now, while performing the experiment, how much ever we try to keep it fast, definitely you leave it on for even a few seconds, the temperature is going to increase. The temperature will increase. So it's very difficult to maintain constant pressure in verifying Ohm's law. Especially when you verify Ohm's law, we know that it's true only when temperature is constant. But it is very difficult because even if you leave this battery on for 10 seconds, this is going to get heated up. And so rheostat is made of a material whose resistance doesn't change much with change in temperature. So that helps in verifying Ohm's law much easier. Okay, children, and then this is good information that it will be good for you to know. Choice of material of a wire. If I need a wire for electrical connections, I'll prefer wire of negligible resistance. So what did I choose? A good conductor, mainly copper or aluminium. If I need a wire for standard resistors means, just now I explained rheostat and all that. Okay, such wires are of high resistance and their resistance must not change due to change in temperature. When you put it in a circuit, its resistance should not change much with change in temperature. So for this purpose, they use alloys like manganese and constantan. Fuse wire we'll be saying later, so I'm not telling now. Filament of an electric bulb is made of tungsten wire. Now it has a unique property. Its resistance is very high and melting point is also very high. Resistance is high and melting point is very high. So it gets heated up to such an extent, to red hot, that it starts emitting light, but it won't melt. If it had have been any other material, if it reaches that temperature, it will melt. But tungsten has this unique feature that its melting point is also very high. Therefore, even it reaches to the temperature where it starts emitting light, it will not melt. Okay, heating element in appliances, again it is made of nichrome wire whose resistance increases. I'm sorry, this will be not nichrome, I'm sorry, not nichrome, constantan or manganese. Okay, this will be of constantan or manganese. Okay, nichrome's resistance will increase with increase in temperature, and therefore it is used as heating elements in appliances. In the sense, your heating rod, your geyser, oven, everything will have nichrome wire because its resistance increases with increase in temperature. Okay, now come to the last part, superconductor. Okay, now we go ahead of this concept we just now saw. As temperature increases, resistance increases, and as temperature decreases, resistance decreases. Okay, now we can use this concept to reduce the resistance of any wire. Now, as you know, though copper is a good conductor, still it does offer some resistance. That's the reason why even a copper wire gets heated up when you leave the bulb on for some time. The copper wire carrying that will get heated up because there is some resistance even though it's a good conductor. Okay, so reducing resistance is a very major problem in electrical connections. So if we can use this concept and reduce the temperature of the surrounding, then its resistance will become very low. Okay, so if the temperature, so now if it is normal temperature, suppose right now if the outside temperature you say 32 degree and the resistance of a particular wire is 10 ohm or 10 kilo ohm. Okay, now I reduce the temperature. Okay, I make the surrounding temperature to 30, then it might become 88 kilo ohm. Like this I keep on decreasing. Okay, maybe at 10 degrees Celsius its resistance will be very less, maybe only 2 kilo ohm. Okay, and if I can further bring it down, maybe at 0 degrees Celsius this particular wire's resistance will be only 1 kilo ohm. And if I can maintain 0 degree or even take below 0 degree, if I can maintain minus 5 degrees Celsius, I can even, the resistance can even become 0 ohms or 0 resistance, which will be really good. Okay, a wire like this which has 0 resistance means it will be so easily, current will be connected, transmitted so easily without any obstruction. So I'm sure that will be a really wonderful thing, that the resistance of anything, if you can reduce it to 0, then you can save a lot. I'll tell you what you save. So this, in this condition, it's called a superconductor. Superconductor. See the definition. A superconductor is a substance of 0 resistance at a very low temperature. 0 resistance, okay, or infinite conductance at a very low temperature. See this example: mercury below 4.2 Kelvin, lead below 7.25 Kelvin, and niobium below, okay, leave off niobium and all, at least remember this, mercury below 4.2 Kelvin are the superconductors. In the sense, if you can maintain a temperature of this much, then the resistance will be completely 0 and they will conduct superbly, and they are called superconductors. Okay, the superconductors are not in common use since it's very difficult to achieve such a low temperature. Okay, so you can remember, you can see 4.2 Kelvin means in degrees Celsius how much it is. How will you convert it into Kelvin? T Kelvin is T degrees Celsius plus 273, or T degrees Celsius is T Kelvin minus 273. T in Kelvin minus 273. So if they say 4.2 Kelvin, it is 4.2 minus 273, that is minus 268.8. Yeah, see the temperature. This, if you can maintain a temperature of minus 268.8 or minus 267 degrees Celsius, which is very difficult to maintain, only in some lab under some special condition you can maintain. If only we can achieve this, then that's a great achievement. Now see, if we can achieve such a low temperature, and because of that if the resistance becomes 0, see, the size of computer could then be reduced to a few centimeter. You will have computer of only this much size, and all the power lines, you see those thick power lines carrying power, they can be just made as thin as a single wire. It's because of the resistance that we have to make thick wires. If the resistance can be decreased, then you can make a very thin wire, and your computer or monitors will become very small. Now this is the future achievement, or people are working, scientists are working on for that. Maybe when you start working, maybe these things can become real. Okay children, with this A part is over, and homework for today will be, okay, written 25th September, question number 16, 21, 23, 24, 25, 27 and 28. Okay, 16, 21, 23, 24, 25, 27 and 28. Plus I had given some numericals also. Okay, not 17, 14, 15, 16, plus I gave one circuit also. So 4 numericals also you will do. Thank you, children.